Greetings, everyone. Welcome to the next session of the LIAMforum. My name is Saleem Ali. I'm the head of Department of Geography at the University of Delaware in the US, and I'm also a member of the United Nations International Resource Panel. And in my role with the UN, I also serve as the lead for critical minerals at the United Nations University's Institute for Water, Environment, and Health, which is based in Hamilton, Ontario, Canada. So given that Canada is the host country to some degree for this forum, I'm happy to make that connection too. So we have a very distinguished panel, so I'm not going to take too much time from them. But basically, the goal of the session is to unpack this very complex issue of critical minerals for the green transition. This is an area which covers both the technical sides of mining and also the geopolitics that are now becoming much more strident as the world considers competition over access to resources. So we're going to start off with the panel presentations. We'll try to keep them to about 10 minutes maximum, hopefully 7 minutes for each panelist. And then the real goal is to engage in a very detailed discussion with the youth, who are the focal point for this entire effort. So our first speaker is Simon Michaux, who is at the Geological Survey of Finland. He also has the status of associate professor. And he has been working with data sets around mineral access and economic geology around critical minerals and challenging the orthodoxy around whether we can actually attain the goals which are being set forward in this regard. So Simon's going to provoke us, I think, with some really interesting data, and then we'll have a discussion with our next two speakers. After Simon, we're going to have Kirsty Liddicoat, who's the Chief Operating Officer of Northern Graphite Corporation. So Kirsty is then going to take us into one particular commodity that's so important for batteries that are going to be needed for the green transition. And that's graphite. And then finally, we're going to have Patrick Nee, who is the co-founder and VP for Strategic Partnerships at Cyclic Materials. And Patrick's going to then give us an overview of how the circular economy might fit into this challenge of sourcing critical minerals and whether we need mining for certain commodities, but not for others. And at what point could we perhaps transition to a completely circular economy? So that's kind of the arc of our session. And so over to you, Simon, for the first presentation.
So, hello. Right. So I've only got one slide. So before I show you that slide, I will probably tell you a little bit about what I've been doing. Please excuse me. So when I left the Australian mining industry and I came to Europe, I wanted to learn industrial recycling and the circular economy. And what I found, though, was there was no credible feasibility plan for the phasing out industrial reform, phase out fossil fuels, replace it with something else. And that really surprised me. And when I looked behind the curtain and I saw how things were, and I asked why this was, I found that across the board, there were no numbers. We simply had not thought things through. So for the last 15 years in particular, we've been using ideology to do our problem solving. Now, normally that's fine. Usually, we have a belief, right? And we all believe in something. But what has to happen is you turn that over to someone to think things through in a practical context, like we're actually going to do this now. This is what we will now do. That has not happened for the last 15 years. So what I found was basic things had not been asked. Very basic question. How many cars were in the global fleet? How many batteries were there that we needed to make? How many hydrogen fuel cells would we have as part of the fleet? Is there a choice between the two? everyone had abdicated responsibility in terms of asking these questions. So then I worked out how many physical units do we need to replace the system as it is now. In the calendar year 2018, how many cars, trucks, vehicles, what have you, and all industrial actions, and then replace that with renewable systems. So everything's now either an EV or a hydrogen fuel cell. All coal, gas, and oil is phased out and replaced with, say, solar panels or wind turbines or hydropower or geothermal. So I worked out a market split of the different energy systems based on an energy IEA prediction of the future for 2050. And then I applied how many solar panels we would need, and how many wind turbines, and how many EVs, and how many batteries, and by what chemistry. All the different chemistries. Again, there was a market split for 2050 where LFP took out most of the heavy batteries. Right. So then I worked out how much metal would we need. So given what I'd worked out, how much metal will we need to manufacture just the first generation, and then put that up against our mining production as it is now? How many years would it take of current mining production to actually get to where we need to go? And followed by, well, if we open more mines, what's in our mineral reserves? And then what's in our mineral resources? And the third question was, what's in our mineral resources under the sea? And the basic question is there enough that we have in hand? The answer is no. Right. And so there's a number of assumptions in there. And the difficulty is the amount of power storage required to manage wind and solar. And so that's one of the blind spots I sort of uncovered. Anyway, so I found that we had vastly underestimated the size of the problem and vastly underestimated the amount of raw materials that we needed. So then I would actually then go to, what do we do? Because my work has actually shown that we have a very serious problem. We can't just ignore this. Okay, can you see that, Ali? Yeah?
Yes, so we can see you. Thank you, Simon. Yeah. Mm-hmm.
What do we do? First, this is a picture I took at a place called Rainbow Beach, the Blow in Australia. So they're my footprints. But the basic idea is, I'm not here to follow someone else's path. Right? Obviously, all paths I've looked at have shortcomings, so I'm here to make my own. But what does that mean? So the existing system is failing. The planned green transition will not work in its current form. But we must attempt to solve the same problems because we must. It's the best game in town. So if the green transition won't work, what will? The circular economy and the steady state economy concepts will need to evolve because they're the only systems that can, with the understanding that we've got to find a different energy system that underpins them. So that's up to us to build a new system. We can't depend on someone else to do it. We can't have ask someone else to magic up an idea and hope that it'll help us. And that new system requires a new relationship between us, energy, raw materials, and the planetary environment. And in closing, I would find that most of the leadership I've come across so far is in a state of paralysis in terms of what to do. So they're not our leaders. Other leaders are going to appear around them to take their place. And when they do, then we can get to work. In the meantime, I'm developing a plan. So that's the end of my 10 minutes. Thank you very much. I'm up for questions.
Okay, thank you so much, Simon. So we can have maybe just one or two quick interventions from the audience. One question I have immediately is sort of just from the point of view of, let's just choose electric cars. Mm-hmm. The transition to electric cars. Can you just give like your elevator pitch on how that might be possible or how it could not be possible?
Well, at the moment, we think we're going to use lithium-ion battery chemistry, right? Yep. And the reserves, mineral reserves that we have in the ground, which are economic deposits that we know of, is less than 3% of what we need for lithium, vanadium, nickel, and cobalt. Nickel's up around 10% and copper's about 20%. Right, so what we think we're going to do, we don't have the physical resources to do it. So obviously what we do is we make batteries out of something else. Now, one of the sodium, the fluoride in your toothpaste, zinc. There are lots of options, right? And the options might even be better, a higher energy density than the ones we've got now. But it's up to us to actually do something. We can't just ask someone else to do all this. The value chain around each of those systems has to be developed. And at the moment, we're assuming the Chinese in particular manufacture all these things. It'll be a market thing. We just give them their money and they give us the stuff and all is well. That kind of thinking will not work for much longer, right? So what will probably happen is a massive contraction in how much energy we consume and how many vehicles we will run until we sort this out. And then we've got to generate the electricity somehow. The solar panels and wind turbines, if we can't solve the storage problem, are not viable in their own form. There are two vectors out of that. There are two solutions to that, but we've got to do them.
Indeed. So, and the hydropower solution in terms of the energy production, but also storage of pumped hydro, is that?
Right. So we store power with pumped hydro most of the time now, where we've got a hydro system and you've got like a reservoir at an elevated altitude, and at night water is pumped into the reservoir and then at off peak, and then during the day at high peak, water runs back down the hill and they generate that power. Most of the suitable sites, there's 530,000 possible sites around the world that have been found. I don't agree the number's that high, but let's say we take that. If you need to actually sort of have a, the problem is how much fresh water are we going to tie up by doing this? The enormous amount of power we need to do this is huge. Is it 28 days buffer, which is 2,100 terawatt hours for the year, or is it 12 weeks, which is probably the closer answer to what really needs to happen, which is many times again. But even 28 days will take up about half of the current freshwater water withdrawal from the planetary hydrological cycle, and there's no way known that's possible. So we can't use pumped hydro. Hydrogen storage, that's the other one we often hear about. The problem is we don't know how to store that much hydrogen or transport it, because there's difficulties there. But then there's the energy involved. It takes 52.5 kilowatt hours to produce a kilogram of hydrogen, and for each kilogram of hydrogen that you get back, you get 15 kilowatt hours of energy, of electricity, when you put it through a PEM cell. So that's 28% round trip, and that's too low. But then there's the sheer volume of what's involved. You can store hydrogen in some circumstances, especially if you're making it from the gas industry. But if we're not allowed to use gas, this is what we've got to do. And so if we were to make enough power to store for, say, 28 days of buffer for wind and solar delivered back to the grid, we would have to expand that power grid by 21%. And if it was, 51%. And if it was 12 weeks, it's 81%. Right, and so now the sheer the problem we keep coming back to is the sheer size of the buffer needed. If we can work out a way where we don't need that buffer, and there is a way through that by developing electronical equipment that can handle variable power, then we won't need the buffer. Then we won't need a lot of those materials. But wind and pumped hydro won't work, stored hydrogen won't work, and my work is showing that battery banks won't work either.
I see. Okay, well, there's the challenge. It keeps getting more challenging. We have two really good questions, actually, but I will come back to them for the full panel discussion, so that because they may well be addressed also by our two speakers coming up. So next we move to Kirsty Liddicoat. Thanks so much, Simon. Kirsty is going to now give us a deep dive into one particular element, carbon particularly, which is used in its allotropic form of graphite as an electrode in a lot of batteries. And Kirsty is the Chief Operating Officer of Northern Graphite. So Kirsty, over to you to tell us about the role graphite is going to play in helping us transition to a more sustainable future.
Thanks, Saleem. What I thought I might actually do is I might start out what about mining in general attracted me, and is that still relevant in this day and age? As I sort of move forward into graphite, I got into mining for two reasons. I love being outdoors. I could camp, I could explore. I've got a geology background, but I also like challenges. And the mining industry has challenges in spades. And we just heard about some of them from Simon. There's the day-to-day challenges on a mine site, but there's these world-changing challenges that as an industry, we need to grapple. And, mining is going to be around for a really long time. So working out how to do it in a way that is actually greener is going to support us all. And what I think about when I think about the big challenges are, tailings. Tailings aren't great. What can we do in that space? We can go to dry stack, but can we go a step further? How do we fundamentally make our waste streams safe, sustainable, and potentially turn them into revenue streams for very low cost? Power. We've just heard the challenge of trying to sustain power. The mining industry uses a huge amount of power, particularly in our processing stages. So what can we do in those stages to think differently, to process differently, to reduce the power that we need? Our footprint. Mining, particularly surface mining, has a large footprint. What can we do to change that? Can we change the way we extract? Can we use different technologies? Can we look at ways to, revegetate faster, quicker behind us? Reducing our impact on the natural area. So not just our footprint, but water, dust, and noise. Particularly in mining, a lot of mines operate in areas where water scarcity already exists. So what can we do to use less, but also leave it cleaner? Often we're taking in dirty water. Can we clean it as it goes through our process and make it useful at the other end for the local communities? And then recycling. And I think we're going to hear a bit more about that from Patrick. But one of the reasons we need to do so much mining is our recycling programs aren't where they need to be. So what can we recycle, both from the end products from where our mining commodities end, but also as we work through the mining process, like everyone else, we have a huge waste stream. And so for me, that's what's really exciting still about the mining industry and why 20 years later, I'm still in it, because I don't get to go outdoors very often, except for on my breaks now. And about 6 months ago now, I was looking to change roles. I'd been in gold, and look, not hiding, I've worked in the nastiest of what we would deem the mining, oil sands and thermal coal. And when I was looking at what I wanted to do next, critical minerals were right up there for me. So I know that critical minerals are needed as part of the green transition. I also know that, we really need to do better in what we do from a mining viewpoint, from sustainability. And that's everything from the environment and the legacy we leave there, all the way through to the communities and the people we work with. And so I decided to come to graphite. Not something I'd actually heard a huge amount about, and honestly thought it was a lead pencil. When you think about graphite, you kind of think lead pencils. But graphite is a key contribution to at least our early phases of the green energy transition through the lithium-ion battery. So graphite is 48% of the anode, and it's about 30% by weight of an entire battery. That's a huge amount of graphite that we need to produce and find. And currently, about 95% of the world's graphite production comes from China. China don't have the environmental regulations that you see elsewhere in the world. And, we are seeing a really big shift away to move into more sustainable areas where we can mine graphite. But it's not just used in batteries. Yes, that's what's going to explode the graphite, but it is actually a key component of the green energy transition. So other areas that it's used, and this is definitely not a holistic list, it's used in solar panels, it's used in wind turbines, it's being used to put into insulation that goes into houses. The biggest carbon emitter on the planet is housing. It's about 40% of the world's carbon. graphite into the insulation reduces that emissions from each house really significantly. It's going into fire suppression systems and ways we can, put out lithium-ion batteries, which is a whole different problem to talk about. And more uses are emerging as we look to the green energy transition for graphite. And the reason for that is graphite is a very lightweight, high heat conductor material, and you can push it into really, really thin sheets. So one of the questions we often get is, what about synthetic graphite? So for some commodities and for some minerals, we can make something that can do it in a way that is less impactful on the environment. Generally, that's not the case with synthetic graphite. And I do say generally because it does depend on the graphite deposit you're mining. But synthetic graphite is made from leftover tar, basically, so oil, heated to really high temperatures and goes through a very energy intensive process. So its carbon footprint is very, very large. It's generally 3 to 5 times larger than a traditional graphite mine. And that's before you think about how we can actually reduce the carbon footprint and the environmental impact of a graphite mine through things like electric vehicles, thermal, solar power, hydropower. So yeah, there is an alternative to mining natural graphite, but the alternative currently is actually worse. One of the challenges we do have though, because a battery, so that 48% of the anode will be generally a combination of natural and synthetic graphite. And the reason for that is synthetic graphite has one property that we need in batteries that we are yet to work out how to manage in natural graphite, and that's its swelling. So graphite will swell, natural graphite will swell, and a battery can only have up to about 5 or 6% swelling before it'll explode. And that's why synthetic graphite is still really key in batteries. Now, we're working on ways to reduce the swelling on natural graphite, because if we do that, we can actually offset the more carbon intensive synthetic graphite. So there's lots of really interesting things that we need to solve, even in graphite, as part of that green energy transition, to really help us reduce our carbon footprint and look at ways that we can actually do what we do in a more sustainable manner. And I'm going to pause there and come back to questions later.
Great, thank you so much for that really panoramic overview, and then a deep dive together in terms of using graphite as a case study, and also linking to this challenge of human synthetic generation of minerals versus mined minerals. And we have this also dynamic with diamonds currently, another form of carbon, where there is this tension between mined diamonds and synthetic or lab created diamonds. So this is, of course, for the youth, it's an important area for understanding the methods, how we evaluate these comparisons between the different elements and how they're manufactured. And we have techniques like life cycle analysis, which can be used to evaluate the differences in terms of impact. So that's excellent. We have time for a couple of questions for Kirsty as well. The one question I had was with reference to the synthetic graphite. The starting material is coking coal, right? Is it?
Yes.
Yeah. So there is still mining involved in that production, which is the other part that often gets missed. And I was wondering if you can say a few words about that in terms of looking at the full cycle.
Yeah, no, that's a great question. We do, because when we think about synthetic graphite, we kind of just think it's made in a furnace, which is broadly what happens. But its raw ingredients are still mined and processed through generally power plants, but anywhere that you put in coal. And we all know that coal in itself is not very environmentally friendly. And that's why we see the carbon footprint of synthetic graphite is so much higher than the natural graphite. Ironically, it's cheaper. And that's a lot to do with the fact that most synthetic graphite is made in China, and things in China tend to be cheaper because labor is cheap, regulations are different. But it does still start with mining way back when. It's just that gets hidden because it's a byproduct of using coke or coal for something else.
Okay, great. Excellent. Well, thank you so much, Kirsty. Moving on then to kind of go full circle, quite literally, with material flows. Our next speaker is Patrick Nee, the co-founder of Partnership for Cyclic Materials, Strategic Partnerships for Cyclic Materials. And Patrick is trained as a mechanical engineer. And he's going to tell us about the work that's being done on cyclicality for meeting the critical minerals challenge. So over to you, Patrick.
Thank you, Saleem, and I'm very happy to be here. I was long ago when I was choosing what I wanted to do with my studies and then with work, I decided that I felt like I had the biggest impact working on technology and attacking specific problems. And if you think about who are the most powerful people over the last 20 years, not actually the presidents of the United States who come and go or the European Union, but it's Steve Jobs, Zuckerberg, Musk, who really are changing the world, and all their engineers that are underneath them. And Simon was telling us about the problems that have to be solved and that we can't look to somebody else to solve them. It really reminded me of the decisions I was making when I was young, when I decided not to go into banking and not to go into some other field, but to use my engineering background to solve really important problems. So I've worked in mining as well, like Kirsty. I was working on copper and some gold production, and recently got very excited about working on the critical minerals that are needed to enable all of our ambitions about electric vehicles and wind turbines and electrifying society in general. And I've gotten involved as one of the co-founders of Cyclic Materials. One of my partner was involved in battery recycling prior to this. And at a meeting with one of the big auto manufacturers, the engineers there said, "You guys are working the right problem. We are very worried about where we're going to get enough materials for the new batteries and where this old battery at the end of its life is going to be thrown away." That's our biggest worry. Our second biggest worry are the permanent magnets that are inside our motors. So we decided to start working on the permanent magnet problem. So permanent magnets are used inside the motors of a Tesla or of a other modern EV or hybrid vehicle to generate the motive power to move the device forward. But they're also used throughout society in various other motors, the starter motor of your internal combustion engine, the motor on your iPhone to focus the lens, the speaker on your iPhone, are all based on magnets made of rare earth elements. And currently, they're recycled at about a 1% level. Well, what's the right level to be recycled? Well, if we look at other metals, the base metals such as iron, copper, and aluminum, they're recycled at roughly a 30, 40, maybe 45% level. Rare earth elements are recycled from end of life at a 1% level. And there's a very simple reason for that. The magnets stick to steel and then they get lost in the slag or the waste of a steel refinery. And we decided to go out and try to solve that problem. So we are taking motors both from old internal combustion vehicles, from consumer electronics, from new EVs and hybrids, and getting the magnets out in a sustainable way, and then returning those magnets back to the raw materials, in a sense, using some magic to unmix the alloy that makes up a magnet to create the raw materials that can go back into the supply chain for the magnets for the next EV or for the next wind turbine. So wind turbines also use these magnets. So we're finding that this need for circularity is broader than just lowering the carbon emissions, which it clearly does, broader than just lowering the water usage, which it does relative to mining, broader than reducing just the land usage relative to mining. But many users of these magnets, i.e. the car companies or the wind turbine companies, are also worried about, as was mentioned earlier, the geopolitical tensions around these minerals. There is a battle around the world for which countries and which industries can control these minerals because they are so key to industry going forward. And so having a local supply of these materials has been of great interest to the magnet manufacturers that are then selling to the motor manufacturers that go into a Tesla or a Mercedes-Benz or a Ford automobile. So our ambition as an individual company is to make enough of these rare earth elements that come from purely recycled sources to power about 6 million vehicles with permanent magnet motors, which are more efficient than any other alternative out there. So we think that one, by preventing these materials from going to a landfill, from two, allowing these motors to be made the most efficient way possible, we're having a very large impact on this transition to an electrified society with new sources of ways of storing energy and hopefully eventually generating it. But it is still just a small portion, and everybody needs to find their little contribution to that in order to make this entire transition, which is going to be challenging, as Simon pointed out, happen as rapidly as possible. So I'm also open for questions when we open the floor to everybody. Thank you.
Okay. Thanks so much, Patrick. Maybe if you can just give us a quick sense of how profitable this business is likely to become. What are sort of, as a businessman, entrepreneur, is it doing well by doing good, or is this going to be more like a social enterprise?
So we are a for-profit company, but I also think if you're going to do something as important and new and therefore risky as this, you really need to be in it, not for the money, but for the excitement and pride in what you're doing. That said, of course, we had to raise funds from investors, so we expect it will be profitable. And our cost of production is lower than the rare earth mines that are the alternative source. So we do believe that when the price of these metals drop, we will still be one of the surviving sources of metals. That said, I think throughout life, you shouldn't be chasing money. You should be chasing things that are impactful and hopefully enjoyable to do on a daily basis.
Okay, fantastic. Well, now we can have our panel reconvene, and I'll start to open the floor for questions and have maybe also a conversation among the panelists so we can all be spotlighted collectively. So there were two questions that came up, and I would encourage the audience to start typing away and putting in more questions. One question which had a lot of positive votes comes from Tara Metters, and the question is, would you view something like a high-speed rail system as an alternative to a car-based future because of the resource problem? And in some ways, this question is also tied to some of the critique coming from the environmentalist community that there is too much of a focus on a particular technology and the growth of EV demand. Should we reimagine our cities or reimagine our future? There was like one report I saw from the University of Technology in Sydney, which was funded by some environmental organizations. And they said that the city of Paris had reduced its car usage by 40% just by having better public transport, bike paths, etc. So are we asking the wrong question, is what Tara is saying. Any thoughts on that from any of you? Simon, perhaps Simon would have, is a victory sign. Yes. Please go ahead, Simon.
So I'm actually part of a group that's actually developing a solution to the predicaments. to meet the boundary conditions I've picked up. And you're right, but something needs to go with it. Now, for example, when we invented the car, the predecessor to the car was the horse and carriage, or the horse and cart. It's the same basic principle. A small vehicle that is parked in our garage, we load up and we transport something somewhere. It's even got 4 wheels, but instead of the car, instead of looking after horses, we're now maintaining an ICE engine. We have this propensity for want magic solutions, which is why everything looks like a Band-Aid on a bullet wound. We want to rip out the ICE and put an EV in its place, and we've got to reimagine. So yes, we've got to fundamentally reimagine our society around whatever our new energy system is, right? And so it's going to be different. Energy systems different, society is going to be different. And so, all right, we have needs. We need to transport stuff. What do we need to transport? People and goods, right? What also has to come with that is we're probably going to have to shrink our system in size and in complexity. So when you sort of say high-speed train system, I'm hearing a lot of infrastructure. I'm hearing a lot of very complex infrastructure, where actually we need to simplify stuff down. So I'm now working on a series of smaller communities. And yes, we do use the idea of communal transport is now much more important than cars. We still have cars, but there'll be much less of them. So all right, we might have, say, buses, we might have, say, trams or buses with overhead wires. Metros are great, but they cost a fortune to set up. Monorails are great, but they cost a fortune to set up, right? So, and it's also really hard to actually sort of put them in existing cities. So I'm cheating. I'm going to a place where there's nothing, and I'm going to build a settlement of about 10,000 people from scratch designed for that. So the infrastructure goes in to move them around, and it's much nicer and easier and cleaner to do that. Right, so to answer your question, yes, we need to reimagine our transport systems, where we can't just put a Band-Aid on the old system and sort of like do a quick change and continue on as before. We've got to change at the center of everything. How do we use energy? How do we use resources? How do we use technology? How do we do transportation? All of it moves all at the same time, and it's got to be merging into the natural environment in a way where we merge with the environment. So it's almost a symbiotic relationship instead of one of exploitation. So we're talking about a fundamentally different human society and a fundamentally different technology chain that goes with it. So I like the idea of using some kind of communal transport, and yes, a train of some sort, but it must be smaller, not bigger. It's going to be slower and shorter range. So we've got to scale back what we want. This idea that we can, jet off to Sydney from Brisbane. It's a nice idea, but how are we going to do it? Right. So I can see a reimagining, for example, of this is what Cuba did in 1992 when the Soviet Union collapsed. I think it was 92. They had to actually go immediately to more communal transport, but the society had to change how it used that transport. They didn't like it, but they did it, and they've come through it, and they're actually a success story now. It's going to be something like that.
Okay, so there is going to be a bit of a paradigm shift, though keeping in mind that we still have 800 million people in the world who don't have access to electricity. There will be a growth in infrastructure still for much of the developing world.
Right. To make another point,
the minerals will be needed.
So sorry to make another point. We want the same solution for 8 billion people. Right, we think there's one solution that's going to be applied everywhere. There are different opportunities in different parts of the world, and there are different needs. Like I live in Finland, and if we don't heat our homes, we're dead. Right, and that's a massive energy cost. But back in Australia, that's not the case. Right, but in Europe, everything's also built up that we can have massive infrastructure for transportation. That's really hard in Australia. So when we go to these areas where there's less stuff there, their solution is going to have to look really different to a solution that has actual industrial capability now. The future's here, but it's not linear, right? It's uneven, but so is the solutions that we apply to the challenges coming in. We've all got very, very difficult challenges ahead of us, but those challenges are different for each region. Don't expect the same solution set to actually work in all areas.
Okay, great. Well, we've now got a sudden like a cavalcade of questions which have arisen.
Oh,
so
shit.
what I'm going so what I'm going to try and do is, given that we have about 10 minutes, I'll try to sum up some of them.
Give the floor to someone else. Sorry about that.
Yeah, no problem. That's fine. So we have one question, and I'll try to combine them, and then we'll go to all the panelists to try and address them. One question is about deep sea mining and whether deep sea mining could provide the sourcing of these metals moving forward. There was a question specifically for Kirsty about what are some ways climate students can address leaders who oppose mining to enlighten them how mining can help with the green transition. Then there's a question for all three speakers. What is the cost per unit of mining raw materials versus recycling? Is the cost per unit of mining cheaper currently? And is that a barrier to why recycling has not been as progressive as mining? I think that one partially was responded to by Patrick, that in most cases, recycling can be cheaper than mining if we just figure out how to extract the material. The main difference there being about the issue, like with the synthetic graphite, is not the same. That's a different question. That's not about circularity. It's about a different kind of source. Then there's a question around looking at resource availability as one factor. Do your assessments consider the changes in demand for developing countries, basically? And that was sort of similar to what I was mentioning. So how do we deal with the North-South problem? And so let's start there. There are also some specific questions about social conflicts, looking at what happened in Nigeria with the Ken Saro-Wiwa killing and how mining companies are getting, they're labeled as often having problems with human rights and so on. So let's just stop there, and I'll let you all figure out which ones you want to address, but try to stay within like 2 to 3 minutes for your segment, so then we can move on. So let's move on to Kirsty first.
All right, let's see how I go. I'll start specifically with the question that was asked around mining companies and how we can educate. Look, mining companies have been historically bad at talking about what we do well. And when something bad goes wrong, social media, it blows up, like everyone knows. And I think there's two avenues. So one, we as a mining industry do need to get better at talking about what we do well and what we're learning, because every industry has things that go wrong. If we learn from it and put measures in place to prevent, then that's what we need to do. But, specifically, we need more advocates who actually understand that mining is part of the solution, but we need to think about how we do it in a more sustainable manner. And so environmental, students are in a perfect spot to do that. You see both sides. You can see different ways of thinking. And so talking about that with lecturers, with people who don't like the mining industry is absolutely key.
Great.
So yeah,
I think one quick question specifically for you, Kirsty, related to graphite also I put in there, is about recycling of graphite, because you didn't talk about recycling opportunity.
Yeah, so graphite is not something that is recycled a lot at the moment, if at all. I think at all. There's a lot of reasons. Often once it's been used, it's contaminated. But we are talking to people around what we can do in terms of recycling. And that mix around synthetic and natural in a battery in particular makes it more difficult. But it is an area where companies are starting to look. And, I do think recycling is, there was a lot of questions there. Recycling is something we should do more of. I think we don't, because historically the mines have been there. But to solve the energy transition, we're not going to have enough of the raw material. We need to use what we have better, and recycling is a key component of that. And I'll leave Patrick to talk about the cost, but he did tell us it's cheaper, and I would probably agree with that once we know how to do it. It's the hump to get there.
Exactly. Okay, Patrick, over to you. And there's also this one question I put in the chat that's more specifically for you, the last one.
Yep. So one of the challenges with recycling is that your product, your feedstock that you're recycling tends to be distributed, have high entropy, to be all over the place. So at a mine, you have a single location where you're digging up your metals. Then at a manufacturing plant, it's all coming out of one plant. But then those products end up from California to Maine to Florida to Vancouver. And a lot of your cost is actually bringing them back in to be recycled. It's the logistics cost of bringing it in. And I think one of the really interesting challenges that could increase recycling in general can be around innovative ways to get harvesting systems in place. Depends, of course, what the product is you're focused on, but harvesting systems are really one of the key steps to a real viable and sustainable recycling business or system. Then there may be technologies, but a lot of these products, once you have the material in-house, there's some way to clean and recycle the material.
So just on that one, the question on extended producer responsibility as a solution, you think it would be a solution, right?
It's really critical. We have much more traction with the European auto manufacturers, for example, than the US ones. The US ones are coming along more slowly, but this extended producer responsibility is felt more heavily in Europe, and we have gotten much more cooperation, much more rapidly out of those companies. I think it's really important that the producers, as difficult as it is to say you're responsible for when Patrick's grandmother throws away some product, it's the only way, or it's one of the ways we can get a system in place. There are probably some other innovative ways, maybe new business models, maybe new technologies, but that's a great problem to work on solving.
I'm so glad you used entropy, because for my students who are listening, I am constantly hammering the importance of entropy as a metric. And I think both of you with our MIT lineage are very much keyed into the entropy question. So thank you very much.
To the question you threw up about, I know just a minute, about collaborating with mining companies. We actually do.
Yes.
We bring our products to a certain point. We recycle our materials to a certain point, and then it goes into, it's a drop-in replacement into the value chain for magnets. Those last steps are mineral processing and separation, for example, of mixed rare earth oxides in our case. So there is a place for collaboration with the metallurgy industry if you're recycling metals, and that's probably true for every other product as well.
Okay, wonderful. Thank you, Patrick. Simon, you have the last word on the questions and sort of coming full circle.
Okay, we'll try and get them all. Let's see. My work looked at a snapshot of how the industrial system was in the calendar year 2018. Right, I wasn't trying to look about what we might grow into in 27 years' time. Is to show that we what we are doing, the direction we're going, is fundamentally flawed. Right, so I wasn't trying to catch growth. I looked at undersea mining a little bit. I'm of the opinion you probably could undersea mine a small quantity, right? But it's going to be very difficult in large quantities up on land to be useful, like 24 million tons of copper. The final answer is this is a dumbass idea, because the environmental impact of mining such a large amount on the sea floor is going to create a sediment plume, which is going to wipe out large portions of sea life in a sea that's already stressed. Right now, and then the question is, does it fix anything? The answer is no, because we don't know. We can't find the quantities needed, right, with what we know. And it's not just a little bit short, it's a lot short. So much so that we should go back to the drawing board and consider something fundamentally new. What was some of the other questions that we've not?
The one about also the developing world. Can you comment on like infrastructure growth in the developing world?
Okay, I did an oil report on oil back in 2019, and I did an estimation. If we brought the rest of the world, like oil's a proxy for economic activity, right? So as oil consumption per capita is a marker of the economic complexity and development of an economy. So if we brought the rest of the entire world into line with what Germany consumed in 2018 in terms of oil consumption per person, and if we extrapolate that to everyone else in the world, we would have to find another 38 Gawa deposits in Saudi Arabia, or an extra 117% extra capacity a day on top of what we have now. So we're not discovering any more oil, not really, right? So what I'm saying is we don't have it in us to actually do to bring the existing third world into line with the wealthy nations. The whole premise behind the modern society is flawed, and exploitation is built into it. And the have-nots are getting very pissed off at the haves. Right, and so the idea of collaboration and cooperation, if we don't clean our act up soon, a very different dynamic is going to take place. So I think the future is going to be, we all go back to the drawing board and we have a fundamentally different way of sharing resources, right? Or we see some very human behavior.
But maybe we can have some what they call, leapfrogging technologies, like like with cell phones, where we didn't need as much minerals, and the developing world didn't go through landlines, and they just leapfrogged to cell phones or something. Right.
That helps some things, but only some. Like all we really need, I don't need my iPhone. I just need to make a phone call and send an SMS. I don't actually need all the exotic technology in an iPhone. Right, so we can go back to the old-fashioned Nokia. True, right. That will help some things, but they're relatively small steps compared to, say, what do we use steel and concrete for? And plastics. What do we do with plastics? These are massive things. They can leapfrog some things, but only if they reduce complexity. And the only way we're going to go for the recycling thing is if we design things to be recycled. At the moment, we don't do that, which complicates everyone's life. And so everything has to shift all at the same time.
Great. Well, thank you so much for our distinguished panel engaging. The audience has been great, and especially my students. We are going to reconvene on Canvas right away to have further discussion. So please sign out and sign in. And the rest of you have a great afternoon, evening, morning. Thanks all to the LIAMforum friends.